Is it recording right now? Yes, I guess so. Okay. Firstly, I'm so sorry about yesterday. I had real technical problems about the internet and the electricity. I had to cancel the recitation hour. But fortunately, we can find another suitable hour for all of us. For those who cannot attend this session, as I said before, I'm going to record the meeting and I'm going to upload it to OT Plus or YouTube, I don't know. Okay, I think you have reviewed the questions. You had approximately 3 or 4 days to review them. I'm going to solve them right now, and if you have any questions, please do not hesitate to interrupt me and ask your questions, okay? Do you have anything right now? No. Okay, let me start with my first question. Let me see it. No. Here. No. Okay. Let G be a group of order 12. The first question. Let G be a group of order 12. Prove that G has a normal subgroup of order 3, or of order 4. Do you have any idea about this question? No? Okay, let us start. First, let us decompose the order of this group. This is 12, and this is 2 to the power 2 times 3. So, to find a subgroup of order 3 or to find a subgroup of order 4, a way is to look at its Sylow subgroups. Okay, Sylow 2 subgroups or Sylow 3 subgroups, because we know that this group has a Sylow 2 subgroup. We know the existence of Sylow 2 subgroups, and we know the existence of Sylow 3 subgroups. And Sylow 2 subgroups have order 4, and Sylow 3 subgroups have order 3. Let us consider the number of Sylow 2 subgroups here. We know that by Sylow theorems. We know that N2, which is the number of Sylow 2 subgroups, should be by 3, and N2 has to be 1 modulo 2. So what are the possibilities for N2? N2 may be 1 or maybe 3, okay? Let me note this one also. NP denotes the number of Sylow P subgroups of G. Okay, what about N3? N3 has to divide 4, which is the remaining part in the order of G, and N3 has to be 1 modulo 3. Okay, these are all coming from Sylow theorems. Okay, so here, if we are going to consider all of the cases, if N3 is equal to 1, then what can we say about Sylow 3 subgroups? We have only one Sylow 3 subgroup. Let us call it P3. Okay? And we know that if Sylow P subgroup is unique, then it has to be a normal subgroup. Effect, let me write it down. A let P be a Sylow P subgroup of G. This denotes the set of all Sylow P subgroups of G, and P is unique if and only if P is a normal subgroup of G, right? Do you know how to prove this statement? You're going to use another Sylow theorem actually. You know the fact that all Sylow P subgroups are conjugate to each other, and a conjugate of a Sylow subgroup is again a Sylow subgroup. You know this fact, right? So by using this one, you can easily deduce that a Sylow P subgroup is unique if and only if it is normal. Okay, if it is normal, then you know that it's unique, and if it is unique, then you know that it is normal. Okay. So in this case, since we have only one Sylow 3 subgroup, this means that Sylow 3 subgroup is a normal subgroup of G. So by the fact, P3 is a normal subgroup of G. And we know that P3 is a non-trivial subgroup, and it is not equal to the whole group. This means that we have found a non-trivial proper normal subgroup of G. And what about the order of this P3? Since this is Sylow 3 subgroup, we know that its order is 3. So one of the cases here, G has a normal subgroup of order 3, comes from the assumption that if we have only one Sylow 3 subgroup. What if we have 4 different Sylow 3 subgroups? Now we are evaluating the second case. If n3 is equal to 4, then what can we say about the Sylow 3 subgroups? Then we have 4 different Sylow 3 subgroups. So let us consider 2 of them. Let P and Q be Sylow 3 subgroups of G such that P is different from Q. So what can you say about the intersection? Should they intersect trivially, or is there something in the intersection of these 2 subgroups? Consider. We are going to count the elements in G. Okay. What is in chat? What is in chat? Dennis is asking whether the case n3 is equal to 1 and n3 is equal to 4 are just the same things. No, it is not, because we may have only one Sylow 3 subgroup, or we may have 4 different Sylow 3 subgroups. So we have to divide the cases. Okay? For example, when we are considering n3 is equal to 4, then we have to deal with 4 different subgroups. But in the other case, we have only one, so we reach the conclusion directly. I think I am not fully understand what you just said. Could you please clarify what you are saying? You can talk if you have opportunity.
Hocam bu sayıları mod 3'ten yola çıkarak bulmadık mı mod 3'te kalanına göre? O yüzden 4 ile 1 aynı olmayacak mı diye öyle düşündüm bir an.
Şöyle düşün. Şimdi biz bu sayının mod 3'te 1 olduğunu biliyoruz. Ama bu sayının aynı zamanda 4'ü bölmesi gerektiğini biliyoruz. Yani burada biz acaba kaç tane Sylow 3 subgrubu var diye bakıyoruz ya. Ya bir tane olacak. O yani grup için bambaşka bir özellik, ya da 4 tane olacak. O da grup için bambaşka bir özellik. Yani bir tane olan grupları da düşünüyoruz bu durumda. Bir tane Sylow 3 subgrubu olan grupları da düşünüyoruz. 4 tane Sylow 3 subgrubu olan grupları da düşünüyoruz.
Evet, anladım. Teşekkür ederim.
Okay. So what were we considering? Okay, consider the intersection of these two subgroups. Okay, we know that the intersection is contained in both P and Q. So by Lagrange theorem, we know that the order of P intersection Q should divide 3, which is the order of P and the order of Q. Okay, because these are Sylow 3 subgroups. So what are the possibilities for the order of this intersection? The order of this intersection may be 1 or maybe 3. Can it be 3?
No, because we pick them to be different.
Yes, since we have taken these two Sylow 3 subgroups as different Sylow 3 subgroups, so they cannot intersect with the all elements, as P is different from Q. So we have concluded that the subgroup P intersection Q has only one element. This means that if you take two different Sylow 3 subgroups and you choose any pair you like, okay, as from Sylow 3 subgroups, then they always intersect trivially, okay? This means that every two Sylow 3 subgroups intersect trivially, okay? So how many non-identity elements you'll get from counting the elements in Sylow 3 subgroups? Count all non-identity elements from Sylow 3 subgroups. Okay, we have 4 different Sylow 3 subgroups, and each has 2 non-identity elements, right? We have 4 times 3 minus 1, which is equal to 4 times 2, 8 non-identity elements from Sylow 3 subgroups. Okay, are you convinced about this? Okay, then we have only 4 elements left. There are only 4 elements. And we know that a subgroup exists since group exists. This means that all of these 4 elements lie in a unique Sylow 2 subgroup. Let us call R. So, since we have a unique Sylow 2 subgroup, this means that this R is a normal subgroup of G. Is the unique subgroup, the unique Sylow 2 subgroup of G, this R has to be normal in G. And we know that since this is a Sylow 2 subgroup, the order of this subgroup is 4. So we have evaluated all of the possible cases, right? We have only 2 cases, which are n3 is equal to 1 and n3 is equal to 4. And when n3 is equal to 1, we have concluded that the Sylow 3 subgroup is a normal subgroup of order 3. And if we have 4 different Sylow 3 subgroups, in this case, we have the Sylow 2 subgroup as the normal subgroup of order 4. Okay? So we have covered all the cases. So we are done.
Hocam bir şey sorabilir miyim? Şimdi N3'ten yaptık ya biz. Mesela N2'den de yapsaydık aynı sonuca ulaşacak mıydık?
I think from the number of Sylow 2 subgroups, it may be a little bit hard to count the elements because we know that Sylow 2 subgroups are of order 4, right? So unlike Sylow 3 subgroups, there may be non-identity elements in the intersection. So you may have difficulties in counting the elements there. Okay, so it is reasonable to choose the Sylow P subgroups where, accordingly P, where the intersection of Sylow subgroups is trivial, if you're going to use the counting argument. Okay, from N2, maybe I cannot see the way right now, but maybe we have to use another method. Okay, if you want to solve this question by using the number of Sylow 2 subgroups.
Yani prime olandan yapmak daha mantıklı diyorsunuz değil mi?
Prime olandan kastın order'ın içinde tek kuvvetle, yani bir kuvvetiyle görünen prime'sa evet. Sayma argümanı yapacaksanız onu kullanmak her zaman daha mantıklı oluyor.
Tamamdır. Teşekkür ederim.
Okay, any other questions? No. Okay, what about the second one? The second question. Let G be a group of order. G be a group of order 231. Okay, prove that every Sylow 11 subgroup of G is contained in the center of G. Is contained in the center of G, which is this one. So how to perform in this question? Okay, how we factorize 221?
Maybe after showing that the Sylow 11 subgroup is normal, we can look at the action G on that normal subgroup, but I'm not sure how to proceed after that.
Yeah. Yes, but the idea is totally correct. You're going to apply the same thing in the solution. So let us consider the Sylow 11 subgroup and see whether it is normal or not. Okay, let's. Okay, and N11. We know that N11 has to be 1 modulo 11, and N11 has to divide the remaining part here, which is 21. Okay, so it has only one possibility, which is 1. Okay, because what are the divisors of 21? It is 1, 3, 7, and 21. Okay, and all the divisors, all divisors of 21 are 1, 3, 7, and 21, and 11 has to be equal to 1. This means that we have a unique Sylow 11 subgroup. So there is a unique Sylow 11 subgroup. Let me call this as P of G. And we know that since this is unique, it has to be normal. And hence, P is a normal subgroup of G. So after considering its subgroup property, to show that it is contained in the center, we should think something in the element wise, right? So we are going to consider the action of G on this subgroup by conjugation, because we know that since it is a normal subgroup, it is invariant under conjugation, right? As P is a normal subgroup of G, we know that G, P, G inverse is equal to P for every G in G. So this means that the action of G on P by conjugation is a well-defined action. So we can consider the action of G on P by conjugation. This is actually a special type of action, and we are going to write down, for our purposes, we are going to write down our homomorphism coming from the action from the group G, which is the group who acts, to the automorphism group of P, since the action is conjugation. Okay. So, and there exists phi from G to automorphism group of P. Niye yazmıyor bu? Şeyi bitti sandım. Homomorphism. Okay, what is this homomorphism? This phi takes a group element G to something like phi sub G, and phi sub G is an automorphism of, this is not G, this is P. It's an automorphism of P, which takes an element from P, which is X, to G, X, G inverse. Okay, this is the action we defined. So, what is the kernel of this action? What is the kernel of this homomorphism? Kernel phi actually contains all G in G such that phi sub G is identity on P. So this contains all G in G such that okay, phi sub G of X is equal to X for every X in P. This is what identity map means, right? So this is all G in G such that G X G inverse is equal to, doğru mu yapıyorum ya? X for all X in P. Okay. So apply first isomorphism theorem. This is very similar to the center, right? But here the set contains the elements from G, not from P. So we have to do something more. So apply first isomorphism theorem. Then G over kernel phi is actually isomorphic to automorphism group of P. by writing this one, not the symmetric group on P, by but automorphism group of. No. This is not isomorphic. This is isomorphic to a subgroup again. This is isomorphic to a subgroup of automorphism. Isomorphic to a subgroup of automorphism group of P. Okay, I think we have no problems here. So, what can you say about the order of automorphism group of P? What is the order of P?
11.
This is 11, yes. So, if you have a group of prime order, what can you say about that group?
Cyclic.
It is cyclic, yes. So this means that P is isomorphic to
Abelian.
okay. So what can you say about the automorphism group of this one? We have found the automorphism, if you remember, in one of our recitation hours. The automorphism group, the automorphisms of Zn is actually determined by the images of generators, right? So this means that the automorphism group of Z11 is nothing but isomorphic to Z11 star, which contains all elements who have multiplicative inverses, right? Because elements who have multiplicative inverses are the generators of these groups. So this means that automorphism group of P is isomorphic to Z10, okay, which is actually Z11 star. Z11 star, the units of this group. The elements who have multiplicative inverses, okay? The elements which are relatively prime to 11, okay? And there are 10 of them, of course. They're all generators. So now we know the order of the automorphism group of P. The order of automorphism group of P is equal to 10. And we have something like this here. G over kernel phi, the order of this group, has to divide the order of automorphism group of P, which is 10. But we know that the order of G is decomposed as 3, 7, and 11. And this group, the order of this G over kernel phi is also contains divisors as 3 or 7 or 11, but at the same time, it has to divide 10. Is it possible? G over kernel phi has to be equal to 1. Okay? Because we have no 2 factors here, or 5 factors here. So this means that this quotient group has to be the trivial group. Okay? So what does it mean? As G over the order of this G over kernel phi is equal to 1, this means that G is equal to kernel phi. What was the homomorphism? Phi G automorphism P, taking G to phi sub G, and this takes an element X to GX, G inverse. Okay? But since G is equal to kernel phi, this means that every element of G acts on P like the identity map. Okay? Phi sub G is equal to identity on P for every G in. Okay? So what does it mean? This means that phi sub GX is equal to X for every X in P and for every G in G. And this is nothing but GX G inverse is equal to X for every X in P and for every G in G. As you see, since this is valid for every element from our Sylow 11 subgroup X, this means that every element from this subgroup lies in the center of G. Okay, this for all X in P is the crucial part. Okay, and this for all, of course. This is a hard question. Okay, not an easy one, but I think it is fun to see such a question in such a course. Do you have the same fun that I feel inside? Okay. Do you have any questions?
May I ask a question?
Yeah, sure. Berk, lütfen.
How are we able to find a homomorphism induced by the action which is whose codomain is not the symmetric group of P but automorphism group of P? Like, why do we define it like that one? Or how do we actually, not why, but...
Okay, since our action is conjugation here, we know that the conjugation for a group itself, for P, in this particular case, the conjugation is an automorphism, right?
Yes.
With its element, it's a conjugation. But since this P is a normal subgroup in our whole group, also the conjugation by the elements from the group itself, not just the elements from the subgroup, also forms an automorphism of P. So there is no harm in defining this conjugation action from G to the automorphism group of P. Okay, because the elements of G, the elements of G, sorry, just 1 second. The elements of G does not provide more elements from the symmetric group on P.
Okay. So it's actually, since these are actually inner automorphisms, I think.
Yes.
Okay.
These are inner automorphisms and P is a normal subgroup. These are not the inner automorphisms of P, but the inner automorphism. Okay. If you define the conjugation from G to G, then this means that you have an inner automorphism of G. But defining an action from G on P does not provide an inner automorphism, but it is something like an inner automorphism.
Yeah, here I think phi G is an inner automorphism, right?
Yes, phi G.
Okay.
Okay. And we are strongly using the fact that the Sylow 11 subgroup P is a normal subgroup of G. Without knowing this fact, we cannot define such an action.
Okay. Okay, thank you very much.
You're welcome. Any other questions? Is everything clear? Yes.
Ben de bir şey sorabilir miyim? Bu otomorfizm P'nin Z10'a izomorfik olduğunu bir daha anlatabilir misiniz? Onu biraz kaçırdım gibi oldu.
Şöyle anlatayım. Şimdi geçen haftalarda bir yerde biz Z'nin otomorfizmalarına ve homomorfizmalarına bakmıştık, yanlış hatırlamıyorsam eğer. Orada şöyle bir şeyle karşılaşmıştık. Dedik ki, if we consider automorphisms of Zn, okay, let us take an automorphism. Let me go. Let F be an automorphism of Zn. And let us take an element X from Zn. Then what we have here, if you look at the image of X, instead of this one, you can write, since we are in an additive group, you can write this one as sums of ones which are in X copies, right? And since this is a homomorphism, instead of this one, we can write f of 1, dot, dot, dot, f of 1, and we have X copies again. So instead of f of X, we have nothing but x times f of 1, okay? And 1 is a special element here. 1 is the generator of, 1 is one of the generators of Zn. So this means that for an arbitrary element x in Zn, its image is uniquely determined by the image of a generator. Okay, so this means that by looking at the conditions on this map, to be able to see this as a bijection, looking at the kernel, looking at the image, then you can conclude that every automorphism of Zn is a map, something like taking a generator to another generator. Okay, so we have 10 different possibilities for this case, for Z11. Okay, because we have 10 generators for this group. Okay, how can we find the generators of this group? We just look at the numbers which are relatively prime to 11, right? So we have 10 of them. This means that we have 10 many different choices for sending a generator from the domain to another generator in the range. Okay, so we have 10 different automorphisms of Z11.
Anladım hocam. Çok teşekkür ederim.
Any other questions? No questions. Okay, third question. Prove that. Prove that. This is the fourth question or your third question?
Hocam ben bir şey sorabilir miyim?
Aha.
Şey demiştiniz ya Z11 star tam olarak ne oluyordu?
Z11 star is a group which contains all elements in Z11 which are relatively prime to 11.
Tamam.
Okay, you can use the same thing for every Zn. Let me write it down. Zn star, sometimes it is denoted by UZN. These are the units of Zn actually. You're going to see this notation, I think, in the ring theory. This contains all x in Zn, which are relatively greatest common divisor of x n is equal to 1. Okay. If you remember, we were using this one to find the generators of this group. These are actually the generators of this Zn, the set of all generators. Yes. For example, if you consider Z5, since 5 is a star, 5 is a star, not 5 is a prime, then this means that in this set we have 1, 2, 3, 4 only. But if you consider, and this is actually isomorphic to Z4, but if you consider, for example, Z4, then this is not isomorphic to Z3 because we have only 2 elements, 1 and 3, which are relatively prime to 4, and this is isomorphic to Z2. But if you have a prime number as n, then this means that Zn star is isomorphic to Zn minus 1. Okay?
Tamam hocam, teşekkür ederim.
Okay, our third question. Prove that a group of order 217 is cyclic. Yes, a group G, let me go. How do we decompose this 217? Let me see. 7 times 31. Okay. We have 7 times 31. So how to show that a group is cyclic? The basic way is to find a generator, but this is an abstract group and we have nothing, no information to deal with elements, right? This is very abstract. So maybe we can use the new method we've just learned, which are the Sylow P subgroups, okay? And you know the internal direct product and external direct product of groups, and we are going to combine these two information. So, what can you say about the number of Sylow 7 subgroups? We know that this should divide 31, and N7 has to be 1 modulo 7. Since 31 is, yes. Since 31 is a prime number, and this the number of Sylow 7 subgroups has to be 1 modulo 7. We have only one possibility for this one, which is equal to 1, because the only divisors of 31 is 1 and 31. And if you divide 31 by 7, we have 3 as the remainder. So this means that N7 cannot be 31. It has to be 1. Okay? Let me first write the candidates here. From here, what we have, N7 is equal to 1 or 31. So combine these two to reach the conclusion that N7 has to be equal to 1. So what does it mean? It means that Sylow 7 subgroup is a unique Sylow subgroup, and so it has to be normal, okay? So Sylow 7 subgroup P is unique and hence normal. Okay, we have one normal subgroup of G, okay? And the order of this normal subgroup is 7. Put aside, you're going to need this information. Similarly, consider the Sylow 31 subgroup. N31 has to divide 7, and N31 has to be 1 modulo 31. Okay? So from here, we have two possibilities again. 1 or 7, but it has to be 1 modulo 31. This means that combining these two, N31 has to be equal to 1. This means that we have also Sylow 31 subgroup as a normal subgroup of G. So, Sylow 31 subgroup. A subgroup Q, let me call, is a normal subgroup of, is unique and hence normal. So what we have here, Q normal in G, and the order of Q is equal to 31. So we are going to combine this one and this two, okay, to reach the conclusion. Now we have two normal subgroups, right? P is normal in G, Q is normal in G. So what can you say about this set P times Q? Is it a subgroup of G?
Yes.
Yes, it is a subgroup, actually a normal subgroup of G. Since both of them are normal, this subgroup, this product is a normal subgroup of G. So what can you say about the order? You know the formula for the order of the product. This is the order of P times the order of Q over the order of intersection of P and Q. We know the order of P. We know the order of Q. What about the order of intersection? What is it?
1.
This is 1. Yes. Why is that so?
Because two different P and Q, Sylow P and Sylow Q subgroups only intersect Q.
Yes, we know that P intersection Q is a subgroup of P, which is a Sylow 7 subgroup, and We know that P intersection Q is a subgroup of Q, which is a Sylow 31 subgroup. So from here, we know that the order of P intersection Q has to divide 7. And from here, the order of P intersection Q has to divide 31. Since 7 and 31 are relatively prime, this means that the order of this intersection is equal to 1. So what is this one? We have 7 as the order of Sylow 7 subgroup, 31 as the order of Sylow 31 subgroup over 1, which is the order of the intersection, okay? But this is nothing but the order of G, right? We have a subgroup of G which has the same order as G. This means that P times Q has to be equal to G, okay? We know that we have two normal subgroups which intersect trivially, and the product is equal to G. This means that since P and Q are normal subgroups of G, P intersection Q is trivial, and P times Q is equal to G. This means that G is isomorphic to P times Q, okay? And we know that P is isomorphic to that 7 because we know that every group of order of prime order is cyclic of order of that order. And this is Z31. 7 and 31 are relatively prime, so this is isomorphic to that 7 times 31. Yes, this is as greatest common divisor of 7 and 31 is equal to 1. Okay? This is why as P is of order 7 and Q is of order 31. Okay? From the internal direct product, we turn it to the external direct product because we know that they're isomorphic, right? Any question? So it has to be cyclic, of course. This is G is isomorphic to Zn, so this means that it's cyclic. Questions? This is a nice question, I think. Yes.
217 olacak.
Ha, sallıyorum değil mi sayıları? Okay. Any other comments or suggestions? Anything not clear? No. Okay. May I leave the first question to you as an exercise because just in an abstract way, it is just the same thing. You're going to look at numbers modulo something, and you're going to compare the numbers. Okay? Do you want me to solve it right now, or may I leave it as an exercise? And write down the solution and publish it on OTU class. Is it allowed? Okay. Up to me. Okay, I'm going to solve it. The first one. Let G be an abelian group. Group of order P times Q, where P and Q are primes with Q is congruent to 1 modulo P. Prove that G has a normal subgroup of order Q, and the number of Sylow P subgroups and NP is equal to Q. Okay? The first part of the question actually asks whether the Sylow Q subgroup is normal or not, right? So let us consider the number there. We know that G is of order P times Q, and Q is congruent to 1 modulo P. This means that P and Q, this also means that P and Q are different primes. So what about the number of Sylow Q subgroups? We know that this has to divide P, and NQ has to be 1 modulo P. Okay. From here, we have NQ is equal to 1 or P. One or P. Yes, this NQ has to be equal to 1. Why is that so? Combine these two. Yes. If this is equal to P, if NQ is equal to P, then by combining with the second congruent, we have P has to be P.
Hocam,
Yanlış.
shouldn't we have NQ is equivalent to 1 modulo Q?
Yes.
In the second one.
Yes, of course. This is Q. This is Q. Soruyu yanlış mı yazdım? Yok. Soru da doğru. Hadi nasıl kurtulacağım bakalım. Göreceğiz.
Hocam yine zaten 1 gelmiyor mu? Çünkü NQ P olduğunda P de prime, Q da prime, ikisi aralarında asal.
Aralarında asal olmaları birbirine böldüklerinde
Evet.
kalan bir çıkmayacak demek değil. Ama yukarıda bize verilen şu verildi ya bize. Onu kullanarak eleyeceğiz o durumu. By using the assumption in the question, Q is congruent to 1 modulo P, we are going to eliminate the case where NQ is equal to P. I hope. Okay. Let us consider. If NQ is equal to P, then this means that P has to be 1 modulo Q. But is it possible? If you have this one as the condition, this means that what does it mean in terms of division? Q minus 1 P divides Q minus 1. Is it true?
Yes.
Yes. Then this means that P is less than or equal to Q minus 1. But here, if this is the case, then what we have, Q divides P minus 1. So from here, Q has to be less than or equal to P minus 1. So this means that sallıyorum bir şeyler ama bir yere varacak diye düşünüyorum. Is it possible? Is it possible?
Hocam P
Yukarı,
eşittir Q'dan geliyor sanırım.
Geldi.
hocam,
Geldi.
if we adapt to this inequality with the inequality above, we
Yes,
get
yes.
a contradiction, I think.
Yes, here Q is less than or equal to P minus 1 means that Q plus 1 is less than or equal to P. And here, from the assumption we have P is less than or equal to Q minus 1. Combining these two, let me put 1 here and 2 here. Combining 1 and 2, we have Q plus 1 is less than or equal to P less than or equal to Q minus 1, which is not the case. Which cannot be the case. So we have only one possibility for NQ, which is equal to 1. This means that Sylow Q subgroup is normal. Which means that Sylow Q subgroup, let me denote it by Q, is normal. Unique and hence normal. Normal in G, and the order of Q is equal to Q. So we have completed the first part of the question. The first part, we're asking to see whether G has a normal subgroup of order Q, and we have found that the Sylow Q subgroup, which has order Q, is a normal subgroup of G. What about the second part? NP is Q. This means that there are two different Sylow P subgroups. Okay. For the second part, NP has to divide Q, and NP has to be 1 modulo P. Okay, we have two possibilities coming from here. NP is equal to 1 or NP is equal to Q. But why it is not 1? Why it has to be Q?
I think if it is 1, then as in the previous question, we can write it as the direct product and it would.
Yes. Okay, we are going to use the condition that I have forgotten, given in the beginning of the question, which says that G is a non-abelian group. Okay, now here, if NP is equal to 1, then Sylow P subgroup is unique and hence normal. So by a similar procedure as in the previous question, G becomes a cyclic group, right? Because we have one and unique Sylow P subgroup, which is normal, and another Sylow Q subgroup, which is normal. And if you consider the product of these two Sylow subgroups, then you're going to obtain the whole group. And by using the same idea in the previous question, you're going to conclude that G is a cyclic group of order PQ, right? Which is abelian. And so we get a contradiction. As G is non-abelian. Okay? It is given in the question. Let G be a non-abelian group of order P times Q. So what is the possibility for NP? This means that NP is equal to Q. So we are done. We have solved the second part of the question. Okay? Any question? Can you take the idea from the previous question to this one to get the contradiction in the case NP is equal to 1? Is it all clear?
Hocam ben şu son anlattığınız kısmı çok anlamamış oldum.
Tamam. Şimdi bak, Sylow P subgruplarının sayısı için 2 tane durumumuz var değil mi? Bu Q'ya bölünecek ve 1 olacak, sayı 1 olacak mod P'de. O zaman 2 tane durumumuz oluyor. NP dediğin şey ya 1 olacak ya Q olacak. Neden? Q prime olduğu için.
Tamam.
Tamam. Şimdi diyoruz ki eğer NP 1 olursa biz Q olduğunu göstermek istiyoruz. Çünkü soruda bize onu göster diyor. Eğer 1 olsa ne sıkıntısı vardı ki bunun diye bakıyoruz. O zaman ne olacaktı? NP 1 ise eğer sadece bir tane Sylow P subgrubu var demek bu. O zaman bir tane varsa Sylow P subgruplar unique'se normallerdir. Değil mi?
Evet.
O zaman bu Sylow P subgrubu normal oldu. Biz şimdi bir önce şeyde ne bulmuştuk? NQ da 1 olmak zorundaydı değil mi? Yani Sylow Q subgrupları zaten hiç koşulsuz normal. Bir tane var sadece. Şimdi Sylow Q subgrubu unique. Sylow P subgrubu unique. O zaman ikisi de normal. Çarptığında G'yi bulabiliyorsun. Bir önceki soruda yaptığımız gibi. İki tane cyclic grubun çarpımı, orderları da aralarında asal. O zaman ne olacaktı? Bu P ile Q'yu çarpıp grubu elde ettiğin için intersection'ları trivial, ikisi de cyclic, orderları aralarında asal. O zaman G cyclic olmak zorundaydı. Bu iki grubun external direct product'ına isomorphic olurdu çünkü. G cyclic demek ne demek? G abelian demek. Ama grupta ne verilmiş? G abelian değil denmiş. O yüzden ne oldu? Çelişkiye vardık. Yani çelişkiye neden vardık? NP'yi 1 aldığımız için vardık. Demek ki NP 1 değilmiş. Zaten ikinci tek olasılığımız da Q kalıyor.
Anladım hocam. Çok teşekkür ederim.
Evet. Any other questions? No. Okay. Ay maşallah bu da. Bayağı. Okay. A group of order 72. 72, yes. The fifth question. As you see, there are a lot of methods to deal with the groups of finite order by looking at their Sylow subgroups and some other special subgroups. You can obtain a lot of useful information about the group itself. Now, we know that every group of order 217 is cyclic, has to be cyclic, right? Now, prove that a group of order 72 is not simple. So for this group, we know that by just looking at its order, we know that there is a non-trivial proper normal subgroup. Okay? So, for this, let us consider some Sylow subgroups. Do you see my, okay. Yeah. Now, the order of G is equal to 72, which is 2 to the power 3 times 3 to the power 2. So, N3 has to be 1 modulo 3, and N3 has to divide 8. So what are the possibilities from here? N3, 1, 2, 4, or 8, but we know that it has to be 1 modulo 3. So this means that we have only 2 possibilities, 1 or 4. Okay? If it is 1, we are done. If N3 is equal to 1, then Sylow 3 subgroup is unique and hence normal. So we are done. Okay? What if N3 is equal to 4? In this case, G is not simple, right? I.e., G is not simple. Okay, what if N3 is equal to 4? Is it also the case that G is not simple? If N3 is equal to 4, we are going to determine this one. Okay. What does it mean? It means that there are 4 different Tamam. Kaydı başlattım. We were going to continue with the case of N3 is equal to 4. Now there are 4 different Sylow 3 subgroups. Subgroups of G. Let Sylow 3G be the set of all Sylow 3 subgroups. Now, what we know about Sylow P subgroups for text P is that all Sylow P subgroups are conjugate, right? And if you consider this set, Sylow 3G, then this actually forms a nice set that we can define an action of G on the set by conjugation, since we know that all Sylow P subgroups are conjugate. So consider the action of G on Sylow 3G by conjugation. Now, since there are 4 different Sylow 3 subgroups, this means that the size of this set is equal to 4. So there exists a homomorphism, since we have the action homomorphism phi from G to symmetric group of Sylow 3G, which is isomorphic to S4 as its size is equal to 4, and taking G to phi sum G from phi from G to sim Sylow 3G, taking an element G to phi sub G from this set to the same set, taking a Sylow P subgroup to its conjugate. Right? Action by conjugation means this one. Now, what is the kernel of this action? Kernel of this action contains all G in G such that phi sub G is identity on this set, Sylow 3G, and this means that G in G such that phi sub G of P is equal to P for every P in Sylow 3G, and what this means is that it contains all G in G, GP, G inverse is equal to P for every P in this set, Sylow 3G. Now, by first isomorphism theorem, we are not always using the explicit definition of kernel, but just as an exercise, I'm just writing, okay? Sometimes we use the explicit definition, but sometimes we're not using. Don't think about it. By first isomorphism theorem, what we have is that G over kernel phi is isomorphic to a subgroup of S4, right? Because S4, the symmetric group of this set, is isomorphic to S4 as the size of this set is 4. Okay. So what we have here, we know that the order of G is equal to 72, and the order of S4 is 4 factorial, which is 24. And we know that this quotient has to divide, the order of this quotient has to divide 24 because it is isomorphic to a subgroup of S4. As the order of G over kernel phi, as the order of G is 72, the order of S4 is 24, and the order of G over kernel phi has to divide the order of S4, which is 24. This means that kernel phi is non-trivial. There has to be something, right? Because if kernel phi is trivial, then this means that if kernel phi is trivial, then G over kernel phi is equal to the order of G over kernel phi is equal to the order of G, which is 72, which does not divide 24, right? So there has to be something inside the kernel. But is it the whole group? Is kernel phi is equal to G? Is it the case? And this means that every element of G fixes every element in the set of Sylow P subgroups, Sylow 3 subgroups. If kernel phi is equal to G, then phi of G is equal to identity on this set for every G in G, which is not the case. Which is not the case. Why this is not the case? Because this means that phi G of P is equal to P for every G in G and for every P in Sylow 3G. This means that GP G inverse is equal to P for every G in G. From here, we conclude that P is a normal subgroup, right? A Sylow 3 subgroup is normal. This means that it has to be the unique Sylow 3 subgroup, but this is not the case. But we have 4 Sylow 3 subgroups. So from here, since we reached the contradiction, this means that kernel is not equal to the whole group. And we have found from the first case that kernel phi is not trivial. Hence, as kernel phi is a non-trivial proper normal subgroup of G, G is not simple. Okay, we are done. So in every cases, we have found a non-trivial proper normal subgroup of G. So G cannot be simple if the order is 72. Any questions?
Hocam bir şey sorabilir miyim?
Tabii ki.
Kernel'ını başta bulurken niye hani o bize yetmiyor şey olduğunu göstermek için da devam ediyoruz. Açıklamıştınız bunu ama kaçırdım sanırım.
Bir daha sorar mısın?
Hani burada niye kernel'ına bu G minus 1 eşittir P dediğimizde daha sonra hani bunu devam ettirdik. Conjugate'ini zaten burada göstermedik mi? Mesela sanırım o soru şeydi, cyclic'ti.
Hı hı.
Orada da devam etmiştik. Siz bir şey demiştiniz ama hani bu yeterli değil demiştiniz.
Şöyle,
Orada da anlayamamıştım da burada da sanırım.
şimdi bak burada kernel'ı bulmasaydık da olurdu. Tamam mı? Biz sonuçta bir homomorphism varsa elimizde, if we have a homomorphism, then we are sure that there is a kernel. Whether it is trivial or the whole group, it doesn't matter, but we have a kernel. Okay? For the purposes of this question, we need to show that this kernel is a non-trivial one and the proper one. Yani burada şimdi homomorfizmaya ulaşmaya çalışıyoruz. Biz normal subgroup arıyoruz ya. Biz şunu biliyoruz. Her normal subgroup bir homomorfizmanın kernel'ıdır. And her kernel'da mutlaka bir normal subgroup'tur. Yani normaldir yani kernel'lar. Kernel'lar normal, normaller bir homomorfizmanın kernel'ı. Bu her zaman var. Şimdi biz burada bir tane grubun simple olmadığını göstermeye çalışıyoruz ya. Simple olmadığını göstermek demek ne demek? To show that a group is not simple, we need to find a non-trivial, proper, normal subgroup. Ne arıyoruz? Bir tane identity'den başka elemanlar içeren ve grubun tamamı olmayan bir tane normal subgroup arıyoruz. Grupla alakalı hiçbir şey bilmiyoruz. Ne eleman alıp yazabilirim, ne bir tane subgrubunu biliyorum. O yüzden önce bir subgroup üretmeye çalışıyorum. Subgroup, hani elimde konkret bir şey olsun istiyorum. So we have looked at the Sylow P subgroups. Ondan sonra da normal subgroup arıyorum ya. Normal subgroup aramak demek ne demek? Bir tane homomorfizmaya ihtiyacım var. Direkt şeyden gelseydi, Sylow 2'lardan ya da Sylow 3'lerden gelseydi her durumda normal subgroup, o zaman bir şey yapmayacaktım ama gelmiyor. Gelmediği için o zaman diyorum ki homomorfizma. Buldum homomorfizmayı group action'dan. Nerede o? Burada group action'dan buldum. O zaman şimdi normal subgroup'a giden bir yolum var. Bunun kernel'ı. Eğer bunun kernel'ı birden farklıysa ve grubun kendisinden farklıysa gene işte G'nin simple olmadığını göstermiş olacak. O zaman kernel'a bakıyorum. Diyorum ki kernel bu. Çok da önemli değil. Yani burada explicit yazmamız önemli değildi ama yazmış bulundum yani. Kullanacakmışım gibi. Sonra dedim ki first isomorphism teoremi uygulayayım. Böldü. First isomorphism ne diyor? Kernel'a bölersen injection'a döner map'in diyor. Değil mi? Birebir olur diyor. Dolayısıyla bunun kernel'a bölünmüş hali şurada. Karşıdaki range grubunun içine giriyor. Girsin. Tamam. Ne biliyorum ben şimdi? Bu G bölü kernel order'ı 72'yi bölecek. Aynı zamanda first isomorphism teoremden dolayı da 24'ü bölecekmiş. O zaman kernel'da bir şeyler olmak zorunda. Ama işte kernel'da ne kadar bir şeyler var? Hani non-trivial olduğunu söyledim. Ama ya grubun tamamı kernel'daysa diye bakıyorum bu sefer. Grubun tamamı kernel'da demek. Grubun tamamı kernel'da demek. Şu demek. O zaman bütün Sylow 3 subgruplarını normalliyor bu demek. Yani bütün şu
İşte hocam burası yukarıdakinin aynısıymış gibi geldi. Hani ulaştığımız şey. O yüzden.
Yok. Bak burada baktığın şey bu kernel'ın içinde hangi elemanlar var? Kernel'ın içinde öyle elemanlar var ki şimdi normalde şu demek istediğini şimdi anladım. Özür dilerim. Normalde şu. Sen bir tane Sylow P subgrup aldın. Gruptan da bir tane eleman aldın. Tamam mı? O Sylow P subgrubunu o grup elemanıyla konjuge ettin. Konjuge ettiğinde aynı Sylow P subgrupta kalabilirsin. Ya da başka bir Sylow P subgrubuna gidebilirsin. Şimdi bu öyle G'leri alıyor ki aynı Sylow P subgrubuna gidenler. O G altında, G ile conjugation altında aynı Sylow P subgrubuna gidenler götürenleri kernel'a koyuyorsun. Ama her G bunu yapmak zorunda değil. Alır başka Sylow P subgrubuna götürür. Alır başkasına götürür. Alır başkasına.
Anladım.
Bazıları sabit bırakır. Tamam mı? Ama bak bu kernel'a koyduğun şey bütün Sylow P'leri kendisine götüren G'ler.
Hocam ama mesela o zaman galiba ikinci soruydu. İkinci soruda da kernel'ı yine tanımladıktan sonra en sonunda tekrardan hani ulaştık ya biz işte her x elemanıdır p falan demiştik.
Aha.
O zaman buradaki de mi aynı mantıktan geliyor? Yani aynı şekil,
Yok.
aynı mantıkla mı devam ettik burada da?
Bak benzer bir mantık ama aynı değil. Bak şimdi bu ikinci soruda yaptığımız şey şuna eksettiriyoruz. Biz eleman bazında eksettiriyoruz burada. Şöyle ki bak G grubunu P grubunun elemanlarına eksettiriyoruz burada. Ama şu anki soruda action'ımız kümeler üstünde. Yani ikinci soruda G grubunun elemanları P'nin elemanlarını alıyor, başka elemanlara götürüyor. Ama bu soruda G grubunun elemanları bu Sylow subgruplarını alıyor, başka Sylow subgruplarına götürüyor. Yani eleman bazında yapmıyor bu işi, subgrup bazında yapıyor. Çünkü buradaki kümenin elemanları subgruplar. Orada eksettirdiğin kümenin elemanları grup elemanı. O yüzden elemanların yerini değiştiriyor. Ama burada kümenin içinde subgrupların var. O yüzden subgrupların içinde değişiyor.
Anladım hocam.
Elemanları
Teşekkürler.
bilmiyoruz yani. Elemanları ne yapıyor onu bilmiyoruz. Yani bir subgrubun içindeki elemanları komple başka bir subgruba taşıyor. Onu biliyoruz. Ama içeride ne kadar değiştirdiğini bilmiyoruz.
Tamamdır. Tamamdır hocam.
O iki action farklı. Yani doğasında evet aynı şey. Ama eksetme şekilleri farklı. Çünkü eksettikleri objeler farklı. Birinde kümeleri birbirine, yani subgrupları birbirine permüte ediyor action. Diğerinde bir subgrubun içindeki elemanları kendi içinde permüte ediyor. Any other questions? Okay, then I'm done with my questions. If you don't have any, then we can end the session. Again, I'm so sorry about the inconvenience yesterday and today. I was lost like 5 minutes and you waited for me. Thank you for that. If you have any questions and you don't want to ask it right now, you just send me an email. Maybe we can arrange another office hour or something like this. Or you can ask your questions on Thursday in your lecture, okay? Most probably I'll be there. Not your instructor, but I will be there. Okay? Then see you.
Hocam bir şey söyleyebilir miyim?
Aha.
Bu çözümle alakalı ben başka bir tane daha çözüm görmüştüm de.
Aha.
Onunla alakalı bir şey soracaktım da.
Tamam.
Şimdi mi sorayım yoksa başka bir zaman da
Şu an
sorabilirim
aklına
yani.
takılıyorsa sorabilirsin şu anda.
Yani eğer müsaitseniz sorarım.
Tabii sorabilirsin. Hı hı.
O zaman hocam chat'e linki atayım, o çözümün linkini.
Ha tamam. O zaman we ended the session. Okay. If you like, you can leave. Okay? Hadi sen at. Ben de record'u durdurayım.
Tamam.